In the grid shown, the distance between adjacent dots in one column and adjacent dots in one row is 1 unit. Determine the area of triangle ABC. Triangle ABC would be 1/2 base times height. The base looks to me like 3. The height looks to me like 2. And therefore that is 3. Determine the area of figure DEFGH. DEFGH is basically I'm assuming a rectangle or square, whatever, subtracting this triangle. So let's do that. So it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, it's a square. Okay, 5 times 5. And then, of course, we got to subtract that triangle, which I believe is the same dimensions as ABC. So 3 times 2. So that's 25 minus 3, which is 22. Determine the area of JKL. Okay, so this is a little bit more hard, a little bit more work here. There's several ways of doing this, but let's just do it the way of making it into a square or rectangle and then subtracting the triangles. So that looks to me like a 1, 2, 3, 4, 5 times 5 square, and then we're going to subtract 4 triangles. So 1/2 base times height for this guy is 2 and 5, and then 1/2 base times height for this guy, which is 2 and 3. 1/2 base times height for this guy, which is 5 and 3 for the dimensions. And when you crunch out all these numbers, if I have done this properly, it should be 9.5. In the list of positive integers 1, 3, 9, 4, and 11, the positive difference between each pair of adjacent integers in the list is 2, 6, 5, and 7. In this example, the smallest positive difference between any two adjacent integers is 2. Arrange the integers 1, 2, 3, 4, 5 so that the smallest positive difference between any two adjacent integers is 2. We basically want a situation where the smallest positive difference is 2, so we can't go below 2. So if we can't go below 2, that means adjacent integers cannot be consecutive integers. Like, for example, if I were to put 3 and 4 beside each other, the smallest positive difference now would be 1, and we can't have 1. The smallest has to be 2. So let's see what we can do. So let's start off with a 1. I can't put a 2 here, so let's put a 3. I can't put a 2 or a 4 here. What are the numbers again? Oh, it's these guys. Okay. So the only choice I have is 5. And then here I can't put a 4, so the only choice is a 2. And therefore the 4 goes here by default. And here I think all the differences are 2, right? That's 2, that's 2, that's 3 actually, and that's 2. So the smallest positive difference is 2. So just got to fiddle around a little bit. Part B, suppose that the 20 integers 1 through 20 are arranged so that the smallest positive difference between any two integers is n. Explain why n cannot be 11 or larger. Well, let's see here. Explain why n cannot be 11 or larger. So they basically what they're saying is that the biggest n can be is 10. All right? And that is representing the smallest positive difference. Smallest positive difference. Well, the key to this question, I think, is to concentrate on the number 10, I believe. And then look at what happens if you put extremes on either side. This list is from 1 to 20, so let's put 1 here and 20 here and see what happens. The difference here is 9 and the difference here is 10. So with the number 10, the extreme differences, meaning the biggest differences you can get, are 9 and 10. So therefore, it can never be greater than 10. Yeah. Regardless of what, it doesn't matter anything else. Like let's say I put 2 here, you say the difference there is 18. but we're concentrating on the smallest positive difference. The smallest positive difference looks like it could never ever be greater than 10. And I think that should be sufficient. That when you put 10 in the middle like that, you can never get 11 as a difference, and therefore n at most can only be 10. All right, well, that takes care of part 1. Part 2 here, find an arrangement with n equals 10 to prove it. All right, find an arrangement with n equals 10. So I've got to arrange all these guys. Okay, so let's start off with 10, and then let's concentrate on what I did. So that's going to be 10. And then we've got to make sure that 10 is the smallest difference. Yeah, because that's what the definition of n is. N is the smallest positive difference. So everything else has to be 10 or greater. Okay. All right, so if everything has to be 10 or greater, I can choose these accordingly. Let's see here. 10 or greater. Yeah. Okay, well, if that is 9, that would be 11. I can't put 10. 10's already been used. That's 19. That's 10. And then 8 would be 11. I think 11s and 10s would be sufficient. 18 would be 10. 7 would be an 11 again. The difference I'm talking about. 17 is 10. 6 would be 11. 16 is 10. 5 is 11. 15 is 10. 4 is 11. 3, well, hold on here. 14. Let's put 14 here. That would be 10. And then 3 would give me 11. And then 13 would give me 10. And now I gotta continue up here because I'm running out of space. 2 would be 11. 12 would be 10. 1 would be 11. And then finally 11 is the only number left, 10. So there we go. So I've created a whole bunch of differences where the smallest difference is 10. I mean, there's a tie. There's several 10s. But they just wanted me to create one sort of arrangement where n is 10, and I did. Suppose that 27 integers are arranged so that the smallest positive difference between any two integers is n. What is the maximum possible value of n? All right. So same kind of story, I think, where you kind of take the middle integer, in this case it would be 14, and see what happens if you put extreme case scenario at the end. Well, if you do that, this difference is 13 and that difference is 13. So what does that prove? That proves nothing really. Okay, they're trying to talk about the maximum possible value of n. Maximum possible value of n, oh boy. That's confusing, right? Because n is the smallest possible difference between any two consecutive integers. And then the maximum is what they're asking for of n. All right. So that means basically that the differences would all have to be, first of all, if n is 13, let's just say, that would mean that all the differences for all the other numbers would have to be greater than 13. And then we'd have to show that there's no way of getting maximum possible value of n. There's no way of getting anything greater than 13. There's no way. Okay, I think that's pretty much how you think about it. So 27, that'd be 13, right? And I'll just put in the numbers instead of talking through it, which would be torture. All right, so this arrangement, I think should do it. Because if you look at the differences, if I can do this math properly, the differences would basically be such that the smallest positive difference is 13. Because all these differences, I think, are almost always going to be 13 or 14 the way I arrange them. And you can, you figure it out. So that means that n is indeed, in this arrangement, 13. But I'm confident that that's the maximum possible value. That you could never get a number greater for n than 13. Because 13 is the, from this scenario, the smallest you could get for 14, right? Sorry, what I meant to say was, in this scenario, because you put 14 with 1 and 27, that you max out at 13 for the difference. And that pretty much gives us a system of creating a pattern or an arrangement, which I did, that shows that n would be 13. For each positive integer n, the Murray number of n is the smallest positive integer, m, with m greater than n, for which there exists one or more distinct integers greater than n and less than or equal to m, whose product times n is a perfect square. For example, the Murray number of 3 is 8, since 3 times 6 times 8 is 12 squared. And it can be shown that it is not possible to multiply 3 by one or more distinct integers that are greater than 3 and less than 8 to obtain a perfect square. The Murray number of 6 is 12 showed why this is true. So first we have to understand this question. It's a little difficult to understand, I think. So let's talk about this. Let's just talk about their example. So you have a number, 3, and then they're saying, what is that's my n, my small n. And then they're saying, what is the Murray number of n? And the Murray number of n is given by the letter m. And in this case, it's 8. Now, why is it 8? And the reason is because there exists one or more distinct integers greater than n, which in this case is 3, and less than or equal to m, which in this case is 8, whose product, meaning multiplying them all together, is a perfect square. So in this case, what they did was they found one distinct integer greater than n and less than m, in this case 6, that when you multiplied n and m, you got a perfect square, and in this case that perfect square is 12 squared. So let's see. So they're saying, what's the Murray number of 6? Well, they're actually telling you it's 12. And that's going to be some perfect square. So they're asking us to show how this works. All right, so let's see here. I think a good way to do it is to break it up into its prime factors, which would be 2 times 3, and then 12 is 2 squared times 3. Like that. You don't have to, but perhaps it would help. So when you multiply these guys, now I don't know how many more numbers I have to stick in here, but when you just multiply this guy and this guy, I'll do it off to the side, it's 2 to the power of 3, 3 to the power of 2. Now, the good news there is that this is already a perfect square, so we have to somehow make that a perfect square. You can do that if you add a 2, but the definition of this whole thing is that the numbers you stick in here have to be greater than the n and less than the m. So our choices are kind of limited. It's only 7, 8, 9, 10, and 11. Those are the only choices we have. So we can kind of experiment and figure this out. Okay, so I'm going to stay away from the prime numbers, because if I put in a prime number, I don't think I'll be able to get a perfect square. So I'm going to stay away from the 7 and the 11. Now this is 2 to the power 3. This is 3 squared. And this is 2 times 5. Now there's no 5 here or a 5 here, so I don't think adding that is going to make it a perfect square. So I'm just going to stick with the 8 and the 9. If I put an 8 here, which is, well, let's just put it up there, and that is 2 to the power 3. That product, let me put it on the side here, would be 1, 2, 3, 2 to the power 6, 3 to the power 2, and that is a perfect square. I believe that is 24 squared. Yeah. So if I had 6 times 8 times 12, that'd be 24 squared. So that works. But I think I can also stick in the 9, because that is 3 squared. And that's another way of doing this. And that is going to be 72 squared, I think. And I think that covers it. The only thing, not that I'm confused, but this is important right here, 1 or more. So that makes me think is that there's different scenarios, which of course I've shown. See, this is the scenario of 1, and this is the scenario of 2. So in the first one, there's one distinct integer greater than n and less than m, whose product is a perfect square. And then the second scenario, there's two distinct integers that are greater than n and less than or equal to m. Interesting. Whose product times n is a perfect square. Okay. All right. I think I understood that. Very one of the more confusing questions to understand, even just to understand it. Okay, let's move on to B here, since we've become experts now. B says, determine the Murray number of 8. Okay, so they're not giving it to us this time. They're just saying, here you go. What's the Murray number of 8? Okay, so in this case we have 8. And then, of course, I have no idea how many numbers I got to stick in there. And then we're going to have eventually an m, which is the Murray number. And it's going to be, when it's all multiplied together, it's going to be some perfect square. Okay. Oh, boy. Is that all they gave me? Huh. Wow. That's it, right? Okay. So I think this is going to be a bunch of experimentation, since I'm not given any clues here. Okay, so let me first write out the numbers that hopefully I don't have to go too far, and then we'll experiment. And there's got to be some sort of system here. Let me just go up to 20 and hopefully we'll get the answer. The first thing is I'm going to get rid of the prime numbers, because the prime numbers I don't think will help us get a perfect square, because you'd have to have two of them. Like if I use 7, I'd have to then use another multiple of 7, which is not going to be the best choice. So I'm going to get rid of the prime numbers. And then let me put all these numbers into their prime factorization, and then that might help. 2 to the 4, what's 18? 2 times 3 squared. That's a prime number. I got to get rid of that. And then 2 squared times 5. Okay. All right, so let's see now. This is 2 to the power of 3, right? This 8. So I've got to get another 2 to make that 2 to the power of 4, and that would be a perfect square. And then, of course, let's see here. 2 to the power of, well, that's got a 2 in here, so let's see what happens if I put that in there. Now I've got 2 to the power of 4 and 5 to the power of 1, so I need another 5. So there's another 5 there. And then that 2 to the power of 2. I think this does it. Yeah, I think this does it. So this would be basically 2 to the power of 3 times 2 to the power of 1 times 5 to the power of 1. And then times 2 to the power of 2 times 5 to the power of 1. And this would be 1, 4, 3, 4, 5, 6. So 2 to the power of 6, 5 to the power of 2. Yeah, that is a perfect square, because it's 2 to the power of 3 times 5 all squared. And this is my n, this is my m, and therefore that is 20. But the definition of the Murray number is the smallest positive integer. So my question now is 20 the smallest situation for this scenario? Well, let's see if I can get anything less than 20 for m. So let's go back to the drawing board. We've got our n, and then we've got whatever, like I said, I don't know how many. And then we have our m, which I don't know, and it's got to be some perfect square. All right, now let's see. So, well, I like that 2 to the power of 1, 5 to the power of 1 for some reason. I'm going to stick that back in there. And then this time I'm going to combine it with the 3, this guy right here. So that's a 15, right? So 3, because this now, these two become 2 to the power of 4, which is a perfect square. And then the 2 5s combine to make 5 to the power of 2, which is a perfect square. If I can get another 3 in here, I think that would do it. Because these two 3s would combine, and this is a perfect square. So there we go. So that means my m, which is this, is 15. So this is basically 8 times 10 times 12 times 15. And that, let's see here, it's 2 to the power of 1, 2, 3, 4, 5, 6, and then 3 to the power of 2, and then 5 to the power of 2. And that's 2 to the power of 3 times 5 all squared. Yeah, so that makes the m 15, and that means that m equals 15 is a better candidate because it's smaller than 20. And I think m equals 15 is the smallest. I don't think you can go anything smaller than that. So the Murray number of 8, which is I think what they're asking, is 15. Prove that there are infinitely many positive integers, n for which n is not a perfect square, and the Murray number of n is less than 2n. Well, we are going to start off with n equals 8k squared. And that is really just 2 times 2k all squared. Now, this is not a perfect square. And that's because the 2 by itself is just 2 to the power of 1. This is a perfect square, the 2k all squared, but 2, if you multiply it, would make it not a perfect square. So they're saying that, first of all, n is not a perfect square in their definition. N is not a perfect square. Okay, so we got that by using this as n. And then now we have to prove that there's infinitely many positive integers n, and that the Murray number of this is less than 2n. Okay. Now, part B of this question, if you remember, we had found out from part B that the Murray number of 8 was 15, because 8 times 10 times 12 times 15 gave me a perfect square, which is 120 squared. So if that's my n, that's my m. So using the same pattern, we can just put some k squareds in there. So instead of 8, put 8k squared. Instead of 10, put 10k squared. Instead of 12, put 12k squared, and 15k squared. And then this basically becomes 120 squared times k to the power of 8, I believe, which is 120 times k to the power of 4 all squared. And this is indeed a perfect square. P.S. Perfect square. Okay, so that means, therefore, that when n is equal to 8k squared, the Murray number m is, you tell me, what's the Murray number? It's this guy, 15k squared. And 15k squared is less than 2n. What's 2n? Well, n is 8k squared, so less than 16k squared, right? This is a valid statement to make. And since, finally, we have to write, since k has infinite values, n will have infinite values. And that should complete the proof.